Radiation in Medicine. Interaction of photons with the body. By Assistant Professor of Medical Physics, Dr. Al-Arif. Energy transferred. In medical physics we are interested in the amount of energy transferred to our bodies. The energy absorbed by the cells may result in damaging and killing the cells in the human. When radiation incident on the body, some of the energy transferred to the body, transferred, part of which is absorbed inside the body, absorbed, and the rest will leave, according to the following equation. Energy transferred equal the energy absorbed plus the energy leaving. Mechanisms of energy transfer from photons. The energy is transferred from the photon radiation to our bodies by one of the following processes. 1. Photoelectric process. 2. Compton scattering process. 3. Pair production process. Photoelectric process. As in the figure. In this process all of the incident photon energy is transferred to one of the inner shell electrons in the atoms of the medium. The electron absorb all the incident photon energy, h-mu, and eject it from the atom which is called photoelectron. The energy of the photoelectron, electron, appears as the difference between the incident photon energy, h-mu, and the binding energy of the electron, e-binding, in the atom and is given by electron energy equal the incident photon energy minus the electron binding energy. Incident photon energy must be greater than the electron binding energy in order for this process to happen. As a result the atoms become ionized, with a vacancy in the inner orbits which is soon occupied by an electron from outer orbits. Electron moves from outer to inner orbit cause the emission of what is called characteristic X-rays. This process will continue until all inner orbits become filled by electrons. For heavy elements like tungsten many characteristic X-rays will emitted. The probability of photoelectric is proportional to the cubic of the atomic number of the atom, Z cubic, and inversely proportional with the cubic of the incident photon energy, h-mu, cubic. Compton scattering process. As in the figure more likely this process happens between 50 kV to 150 kV photon energy in soft tissue. It happened when photons interact with an electron in the outer shell, almost assumed as free electron. As a result, some energy is transferred to the electron which is then ejected with kinetic energy outside of the atom. The rest of the photon energy, h-mu-, appears as scattered photon with less energy than the incident photon. X-ray with wavelength lambda strikes an electron, assumed to be free in an outer orbit. The photon scattered away from its direction of motion with wavelength lambda- while the electron receives an impulse energy and begins to move with kinetic energy Ke. The photon loses an amount of energy in the collision and this energy appears as a kinetic energy, Ke, for the ejected electron. Electron kinetic energy, Ke, equal h-mu minus h-mu-. The scattered photon has a wavelength lambda-. The difference between the wavelengths of the scattered and the incident photons is given by the following equations, where phi is the angle of the scattered photon, as in the figure. Pair production. As in the figure in this process the photon energy must have energy of 1.02 MeV or more for this process to happen. The photon is totally absorbed in the field of the nucleus without interaction with any electron. As a result an electron, negative electron, and a positron, positive electron, ejected out of the nucleus each carrying energy of 0.511 MeV. The kinetic energy carried by the two particles is given by h-mu minus 1.02 equal kinetic energy for electron plus kinetic energy for positron, the annihilation reaction. As in the figure this process is related to the pair production process in which the ejected positron after losing most of its energy by interaction inside the medium combines with another surrounding ordinary electron. The two particles vanish and two photons appear moving in opposite direction each carrying energy of 0.51 MeV. This process is called annihilation reaction.